Boom, boom. All right, so hello everybody, and welcome to a meager and surface level flyover of the science and art of cryptography. Using what you learn here today, you will almost definitely create encrypted message that will stand uncracked until the sun explodes, or we actually make a working quantum computer, whichever happens first. That said, I will warn you, we will not remain in the realm of Caesar for long before delving into the mathematical parts of cryptography. So, you know, if math disturbs and upsets you, perhaps you'll get your cue about halfway through the presentation that you should step out. But I will cover some of the fun classical stuff first. So we'll kind of just cover both. But the punchline of this presentation is kind of elliptic curves and how they're used in practice. So we'll get to that. The check-in code is CRITPO, not crypto. There it is in the bottom left-hand corner, CRITPO. I assume that was unintentional. I didn't make the code, but if you want to check in with that, you're going to want to go down to acmucsd.com and log into our members portal, and you can turn in that code for points. And then eventually, in a million years, when the dev team finishes the store, you'll be able to redeem those points for things like prizes and maybe like a cyber sticker. Actually, oh my gosh, I have them this time. I actually, because I just moved, so I know where all my stuff is. Boom, look at these things. Oh, it's yeah, you can kind of see. I'm trying to get it to not block, but I've got literally like 500 of these stupid stickers in my binder. I can put it up here by the one that's hovering. Anyways, so yeah, I'm gonna get rid of these soon. As soon as we start having in-person events, week one, winter quarter, you should come on down to, I believe, Henry Booker room. I'm gonna be in there. I'm gonna be handing out those stickers to anyone who comes looking cute or whatever. All right, so moving on. Yes, this workshop and its contents, obligatory plug, are brought to your screens by ACM Cyber at UCSD. ACM Cyber is a special interest community of the largest technology organization at UC San Diego, the Association for Computing Machinery at UCSD. You get the idea. We have over 400 members. We're org of the year. We do a bunch of CTF related things, and we like to teach you to hack. That's basically all you need to know. So stop by our Discord later if you're new. But for now, let's just hop straight into the crypto. I lied. We're hopping into me. You're probably wondering how I got here. My name is Aaron, and I've been a user of military-grade encryption for quite some time now. I used to do some presidential work for ACM Cyber, but now I just handle the money sometimes. My greatest ambition is to one day graduate. We'll see if that ever happens. Today's fun fact is that as of now, I've set several new records for caffeine ingested by a single person without noticeable heart palpitations. Please drink lots of water, as I totally am. There's my water. Okay. So quick shout out to Triton Software Engineering. This workshop was originally a collaboration between myself, associated with ACM Cyber, and Triton Software Engineering by lieu of David Hacker. David Hacker, which is an awesome name to be helping me give a cyber presentation. He could not be here today, but I will be using a lot of his content. So shout out to him for being awesome. And we'll go ahead and jump right into it. So here's the quote I would like to start with today. The quote is, "Good crypto is a hacker's worst nightmare. Bad crypto might as well not exist at all." This is a quote by the person I often quote, Yifan Liu. I think I've quoted them 3 consecutive times in all 3 of my workshops this quarter. They were the person that cracked, one of the persons that cracked the cryptography on the Nintendo 3DS. They have a really good write-up, and this quote is literally in that write-up. So yeah, I like them. Anyways, so here's a quick overview of what we're going to be jumping in today. This is the breakdown. We're going to kick things off with a little bit of a classical touch, talk about cryptography used historically and whatnot. We're going to jump into what modern cryptography looks like at a very high level, just public key cryptography, basically. And then we're going to jump into an application of public key cryptography, which is known as elliptic curves. They're very curvy. So starting off with the classical breakdown, we have some romantic beginnings, of course. While not the world's first, certainly the world's most famous, the cipher personally used by Julius Caesar to communicate with his troops is an oft-cited example of a substitution cipher, where all the letters in your message have a direct one-to-one translation into a different letter. The Wikipedia example of this is attack at once. And you would translate each of these letters into something like this. So if you intercepted one of Caesar's messengers, you would get the message EXXE. Well, I mean, you get the Latin equivalent of those letters. I don't speak Latin. But you would get those letters and you would have to basically cry because you don't know what encryption is. In any case, it's not a very strong encryption. So if we look here, it relies more on obscurity rather than security. Because after all, the way it works, and you kind of saw from the wheel here, you basically have an offset. You have two alphabets and you offset them by some shift value. And that tells you what the translation between the different letters is. So for really, there's only 26 different shifts that you can use, right? You have an alphabet and then you have a shifted version of that alphabet. In this case, we've shifted it over by 4 letters. So what is A is now E, and so on and so forth. And you'll also notice that when we run out of letters in our shifted alphabet and get to Z, we start over again with A, B, C, D because they haven't been used yet. And you that kind of makes sense if you look at the circular dial, right? You come all the way around to Z, and then what's the next letter? It's A again. So it's in a way, it's the world's first Modulus modular style cipher, which is to this day how a lot of ciphers do work behind the scenes. But of course, the easiest way to crack this, if you understand vaguely how it works, is you simply try all 26 options and then see what the shift looks like, because you can very quickly find out from cues that you're going to find it very quickly. It's important to note that even this trivial cipher has a key that is supposed to be required to read and write it. Does anyone know what that key is? Every cipher ever has a key, a piece of secret knowledge. 4. Nick is right. The key is 4. If you know that the shift is 4, you can crack this cipher very easily. If you don't know the shift is 4, you can still crack it very easily, but it might take you 5 extra minutes. So it was not 3.999. Okay, so let's generalize this a little bit. We're interested in understanding not just specific examples of cryptography throughout history, because we could go into like World War II cryptography and all that kind of historical stuff. But I'm interested in taking this very basic example and using it to get to elliptic curves. I'm literally going to one-to-one bridge the gap, no intermissions. It's going to be hilarious. So let's go. Yeah, I'll let Ishan cover the discussion on Enigma machines. Okay, so if you generalize the Caesar cipher, you get the general substitution cipher. This is a little bit better. Instead of having a shifted alphabet, you literally just randomly rearrange the letters in your shifted alphabet. So instead of it being in the same order as the regular alphabet, your letters could be in any order. And this is beneficial because you get about 26 factorial different shifts that you can use rather than 26. 26 factorial is a significantly larger number than 26, right? So here's our basic alphabet, and then here's some random scrambling of it. It's not like it has a shift, because it's just in some order that you would have to know ahead of time in order to be able to decrypt it. Well, so this is great, right? Like what else could we do? Because after all, like how would you crack 26 different, we can't try 26 factorial different options. So that's it. This is the perfect cipher. There's no way to, yeah, Nick has it. You have to do frequency analysis, because the problem here lies with the fact that the relationships between your letters are still one-to-one, right? So in your original cipher, I don't know if you can see my mouse at all. It's probably small, but I'm hovering it over the E. If you can see the mouse. Okay, great. I will continue to use this trick. So you have an E that translates to an L, right? And so you're going to look at your ciphertext that's going to have all the same letters that you would have in your regular alphabet. The only difference is that the most common letter is almost definitely going to be L, because that in and of itself just follows from the fact that E is the most common letter in the English alphabet. So L, its ciphertext version, will become the most common letter in the ciphertext alphabet. So using frequency analysis, what we know about how common letters are in English, we know that whatever ciphered letter is most common is probably E. Second most common is like T or S or whatever. And then from there, honestly, just having 3 correct guesses for a letter is usually enough to use context and other clues to completely crack open the rest of the message. It's pretty embarrassing, actually. So yeah, there's automated tools that do this, and like that, it's pretty easy. So even with having 26 factorial different keys, it is not enough. It is not nearly enough to be able to crack this, and that's disappointing. So let's see what the generalization of this is, right? The next step up from this is a Vigenere Cipher. So instead of having, oh, by the way, what's the key in a general substitution cipher? Last time it was the shift of 4, but what's our secret key, so to speak? Some permutation of A to Z. That's totally correct. So if you wanted someone to be able to crack this, they would have to receive the entire shifted alphabet, and that permutation tells them how to unshift it. Or they could just do frequency analysis, which might literally be faster than having the ciphertext. So Vigenere Cipher, before the key was kind of this permuted alphabet, let's have the key be some kind of phrase. So in this context, I'll pick cyber. Now with this cipher, the ciphertext depends on both the value of the character in the sentence as well as the position of it, right? So in this way, you have a non-one-to-one substitution cipher. Let me just show you how it works. So if you take the word cyber, right, and you translate each letter into a number, C is the 3rd letter of the alphabet, so that would be 3. Y was the 25th letter of the alphabet, so that would be 25. And you kind of get this like this offset of 5 numbers. You can offset each letter in the original plain text by that much. Now, instead of having a cipher alphabet, you're literally using the word cyber over and over again. But now, instead of just translating, you are adding the value of C to the letter of A. You are adding the value of Y to the letter of T. And so you'll notice that this has a really cool effect of, despite the fact that in the original text, the letter A appears in multiple places, 3 places actually, right? We have the first one, the 4th one, and I think the 6th one. It translates into C, or it translates into E, or it translates into Y. And so what's really cool about this is now you can't do frequency analysis, right? You're basically good to go, because now, even if E is the most common letter, it gets translated into one of 6 different things once it actually gets sent back down to the final ciphertext, right? So this is perfect, surely. There's no way you could possibly crack this. You need to have the keyword cyber in order to crack this. Does anyone disagree with me? I'm claiming this is a perfect cipher that can never be broken. And I'm claiming that we have solved the frequency analysis. Yes. So Zenas, again, gives us great advice, which is if you can guess the length, you can still do frequency analysis for every 5th letter. I believe it would be every 6th letter, just because cyber is 5 letters, so C would appear every 6. Anyway, you get the idea. So the frequency analysis can now be applied every 6 letters, which lets you basically, like in a short message like this, it's not really going to help you much to crack the message. But in a longer message, which is, most useful messages are going to be, several sentences long. A small key phrase like cyber is going to be cracked open by this kind of frequency analysis in no time at all. It's trivially easy. Furthermore, if you can guess some amount of the plain text of the message, or if you can guess a subset of the key that's being used, this cracking process takes almost like exponentially less time. You can do it even faster. If you ever take Math 187A here at UCSD, you will do exactly this as part of several of the homework assignments. By the way, take that class. It's fun. Yes, have fun, Ishan. You'll have a great time until you get to B, and then you'll stop having a good time. So let's extrapolate this out to its logical conclusion. If the problem is the shortness of the key, then let's just make the key as long as our message, right? And this is called a one-time pad. So assuming we have the message attack at once, let's have a new key that is exactly the length or even longer than our message, such as cyber is yummy. Now, if our password is cyber is yummy, then our encrypted text is this. And I claim that this is literally unbreakable, that there is no way to know the original plain text without the cipher. That is what I claim. No, Marcello, listen, brute force doesn't even work. Brute force does not work because you can brute force the key and create any potential message you want, right? You can, there is some pad that produces the message, come to my tea party, rather than attack at once. You have no way of distinguishing between a correct key and an incorrect key. It is actually, I'm not like attack it twice. I am not trying to like fool you this time. This really is perfect secrecy. That is the technical definition of it. If you have a one-time pad that is as long as your message, there is no way to crack the original message. It's completely unbreakable. However, you might notice from the name that there are some drawbacks to using a one-time pad. For one thing, you can only use it once, because if you use it more than once, if you use it on more than one message, then well, essentially what you have is a Vigenere cipher, where you take the two crypto messages, stick them together, and then take the same pad and repeat them one after the other. And essentially you're back to the Vigenere problem where you can do frequency analysis again, right? And the more times you use that one-time pad, the faster it's going to be to crack that thing. So that's one major problem, but there's actually other problems. For example, problem number one is that you do need a pad equal in length to the actual secret text. In practice, this is completely unreasonable. Imagine I'm trying to send you a movie that I illegally pirated, and I'm sending it to you through the internet, and it's 10 gigabytes. Well, in order to do that secretly with perfect secrecy, I would need to also send you a 10 gigabyte one-time pad, right? That is completely unguessable, random, perfect entropy. Yeah, it's just going to be a mess. Essentially now everything you need to do is going to require twice as much bandwidth. Not to mention the logistics of actually transmitting that pad is now insane, because if I can transmit a pad to you without anyone else seeing, then what do I need cryptography for, right? I could just send you the message directly, because the message is no less likely to be seen than the one-time pad. So it doesn't matter. And also, again, if someone intercepts the pad itself, all the messages I've ever sent are now usable, or viewable, I should say. So in practicality, this doesn't really help us. However, it does identify these problems for us, and trying to solve these problems is what gave birth to public key cryptography. And so from here on out, we're leaving the domain of the classical and we are entering the domain of the modern. And I say modern, but in truth, a lot of modern cryptography was kind of invented, air quotes, before computers really took off. We're talking like the 70s. So yeah, computers were a thing, but they weren't really like well established or anything like that. They were not widely used. They were not in every home. And the need to encrypt information was really kind of like a government thing. But this problem of trying to figure out how to send a key such that it being intercepted is not a problem is one that kind of gave birth to everything that your computer now uses. You're using it right now to stream to me on Zoom. Everything uses the public key cryptography. So let's jump into kind of like maybe a classical demonstration of what that looks like. So the stereotypical example for public key cryptography, or actually I should say private key cryptography, because we're still on private keys, is this example utilizing a character Alice and a character Bob. And then our eavesdropper is named Eve, and Eve is trying to intercept communications between Alice and Bob. However, for anyone that has ever taken a cryptography class, this is an incredibly boring topic because Alice and Bob is the most overused example of all time. While it is effective at illustrating the different constructs or concepts in cryptography, I think it's not very interesting, and you're in danger of falling asleep if you've maybe seen this lecture before. So instead, I'm going to make it a little bit more interesting. We're going to throw out these characters. We're going to throw out those Alices and Bobs. So this is Bob. And Bob is trying to send a secret message to Alice, and this is Alice. Bob is in love with Alice, and Bob wants to express his love to Alice via some kind of message that cannot be intercepted. Why does Bob care about his message being intercepted? Well, because Alice's dad is watching at all times. He is looking at the communication channel that Bob and Alice are using. And so therefore, Alice and Bob need to use encryption in order to send secret messages between each other. So in the world of public or private key cryptography, also known as symmetric encryption, the way that this would be done is you would take your plain text, and then you would take your key, which let's say we're using a OneTime Pad. So we've got perfect secrecy, and we create a perfect ciphertext that cannot be decrypted. But in order to decrypt that ciphertext, Alice needs that same key, right? In order to get back the original plain text. These keys are the same key. There's no way to send different keys, right? So I need to somehow send the same, not only the ciphertext to Alice, but Alice also needs my key. But then we run into a problem, right? That problem is, of course, the dad. The dad, if Alice is going to see the key, we can assume that the dad will also see the key. And again, we can't rely on obscurity here. Let's say Alice's dad has a PhD in mathematics. He will 100% figure out how this key is going to decrypt into the plain text. We need to keep the key from him. That's the only way, but we also need Alice to have it. So it's kind of like this, this chicken egg situation. We don't know how to resolve this. In other words, how do we agree with Alice on a key, but without sending the key to each other? And the answer, of course, is asymmetric encryption. If we can come up with some kind of encryption scheme that uses a separate public and private key, a separate key for encryption and decryption that are different, and most importantly, cannot be recovered from each other. So even if I had the purple key, I couldn't get the orange key and vice versa, then this could solve our problems, right? We would call the orange key the private key, and we would use that for encryption. And we would call the purple key that's being used for decryption. Oh, excuse me, it's the other way around, I think. Yes, okay. So you use the public key for encryption, and you use the private key, the purple key, for decryption. The semantics aren't that important, but it'll make more sense in the context of the example. The point is that what we're going to send over is the public key. And so the dad will see the public key, but it won't matter because that won't let him decrypt it, right? He still needs the purple key. So we do need to protect the purple key, the decryption key, the private key. But the public key, the dad can have it all they want. We don't actually care. So how can we use this to send secret messages? Well, it's quite simple. Alice and I have to kind of collaborate a little bit. So I have my two keys. We're both using asymmetric encryption. So I have my public key and I've got my private key. Alice has a public key and private key of her own. And Alice gives Bob her public key, but keeps her private key secret. She's never given it to anybody. And so in that process of giving me her public key, I have it, and so does the dad. You know, because anything that we send is going to be seen by the dad, so the dad has it. So I used the public key that I received from Alice to generate a ciphertext. And you'll notice the title changed to DiffieHellman Paper. This technique was described in a paper called the DiffieHellman Paper. So that's why it says the DiffieHellman Paper, which describes specifically this procedure. So if I use Alice's public key to encrypt the message, I can then send over the ciphertext. Now you'll notice that Alice can now decode her message using her private key, which she still has. She never sent it, right? And so she gets the plain text and of course instantly falls in love upon seeing Bob's heartfelt words decrypted before her eyes. Whereas the dad, of course, is stuck with both the ciphertext and the public key, but doesn't have enough information to ascertain the original plain text. And then, of course, if Alice wanted to reply, she would use the exact same process using Bob's keys. And through this way, Alice and Bob have managed to communicate without ever trading information that could be used to incriminate each other. We're not gonna draw attention to that, Marcelo. Okay, so thank you for sitting through my fun little example here. We are moving on. The DiffieHellman paper, something I promised to talk about. It was basically a formal proposal for asymmetric encryption as a theory in 1976. But what was hilarious is that the paper actually lacked a practical implementation. They didn't have a suggestion for what the function that would allow you to create the public and private keys would be. And basically, in order to do that, they determined that they would need a trapdoor function, which is a special mathematical function that is extremely difficult to go backwards, right? So it's easy to go forwards, but it's very difficult to go backwards unless you have the additional information, which is the private key, right? So in order to make all of this work as determined in the DiffieHellman paper, you need this trapdoor function of some kind. Now, as it turns out, since 1976, we have come up with lots of trapdoor functions. Here are some possibilities. So this is actually a quiz. Go ahead and drop in chat A, B, C, or D. Which of these, and if you aren't familiar with them, don't worry. I'll go ahead and reveal answers and kind of cover what they are afterwards. But for those of you that do have a little bit of cryptographic knowledge, you can show it off now. Which of the following are mathematical trapdoors, whether or not they're used in cryptography? So we have A, prime integer factorization, B, the discrete logarithm. There's no poll. You just have to drop it in chat. I'm not going to create a poll this time, unfortunately. So you just have to drop it in chat. Lattice problems and all of the above. So if it wasn't obvious from the flood of messages coming in from the chat, I wish I could do polls, but like it literally won't let me. I have to create them in advance. It's annoying. I don't do it. So we're going to be doing this the whole time. So as you may have guessed, the correct answer is in fact D. If you answer D, you are less wrong than everybody else. Prime integer factorization is used in the RSA algorithm, which is probably still the most commonly used public key cryptography scheme. Examples of the discrete logarithm problem are L-gamma, which isn't really used anymore because of some issues, and elliptic curve cryptography, which is, of course, the main topic of our upcoming discussion, which also uses the discrete logarithm problem, or a specialized version of it. And then lattice problems are very complex. I think Ishan can probably give a great talk on lattice problems, since it's kind of this merger of cryptography and quantum computing. Both prime integer factorization and the discrete logarithm problem are both easily, or I shouldn't say easily, more easily solvable by a quantum computer than a regular computer. However, lattice problems remain difficult to solve even with a quantum computer. So lattice problems are probably going to be the cryptography of the future, so to speak. And examples of this, there's an algorithm called New Hope, RLWE and TrueCrypt. I've never done research on this. So literally, like, I couldn't tell you about this stuff. It's very difficult math. It is very difficult math to understand lattice cryptography. So I don't claim to, but maybe I'll do a lecture on that some other day in collaboration with Ishan. Okay, moving on. So we finished our discussion of public key cryptography. We finished, we're done. Now we're going to talk about one of those examples. I am now excited to bring you into the curves discussion. So thank you all for sticking it out. We literally lost no one. That's so shocking to me. It's like 7 p.m. on a Monday. What's wrong with you? Let me drink some coffee. I'm just kidding. I love you all. Please stay. Okay, so let's jump into elliptic curves. I've warned you there was going to be math, and boom, here it is, math. Cower and terror. So here we go. This is all elliptic curves. It fits on one line. It's written in like 10 characters. It's really not that complicated. It's this simple equation that might not look out of place in like a pre-calculus textbook. It's A and B in this case are constants, but Y and X kind of behave like you would assume when you graph it. So speaking of which, let me show you some examples. By the way, this is the form of an elliptic curve. If you have a function that is in this form where A and B are some number, then that function describes an elliptic curve. That is the definition of an elliptic curve. And depending on what you pick for A and B, you're going to get different curves, kind of. They can kind of look a bunch of different wacky ways. They don't behave like parabolas in basic algebra, but you'll get a chance to play with this yourself and kind of maybe get a feel for what it is. In my attempt to try and give you a feel for the dark magic at play here, I like to think of the A term as kind of the strength of the curve or how much it's being pinched, right? Where the B term is kind of like the length of the string being used to trace the curve. It makes almost no sense until you see it. Trust me, trust me. I'll have the demo here in just a second and you'll be like, ah, that's actually a perfectly valid description. And then finally, there's this third value that isn't in the function called a modulus, which we'll talk more about in a moment. We have to maybe play around with curves for a little bit. But basically what it lets us do, the modulus talks about, helps us restrict the size of the numbers that we're talking about. So we don't have to deal with millions and billions of digits and all that kind of stuff, which would normally happen with an unrestricted function. So let's go ahead and pull out a demo. This is a demo that will allow you to mess around with elliptic curve parameters, change the shape, and also get a sneak peek at point addition, which is an important concept in ECC cryptography. Wait, that's redundant. Never mind. Yeah, so it's acmurl.com/hotcurves if you want to pull this up. I also already have it pulled up, I believe. No, I don't. Let me quickly do acmurl.com/hotcurves. There you go. So this is the exact same page. I assume you all can see this, by the way. Let me know if you can't. But you can mess with A and B independently here. Remember what I said about A being like how much it's pinched, like the strength of the pinch? When you play with A, you really can see it. It's like when A is big, you don't pinch it at all. But when you make A smaller, you're pinching it more and more and more. And then the other thing that is interesting to note is that when you adjust B, it also kind of affects the pinch, but it's almost like if I had a string that was in the shape laying on a table and I like pulled both ends of the string, it would kind of contract like this. It would kind of, basically it's like down here, it's a very tight shape. And then as I pull it, the string basically gets shorter and is pulled away. So that's my very layman's way of describing the effect that A and B have on the shape of this curve. You'll notice that if A and B are set in such a way, you actually end up with what's called a donut here. That's the technical term. You get two curves, but you'll notice ECC is still possible on these curves. And really the only elliptic curves that are illegal, so to speak, are, let's see, probably, let me see if I can find a good example. I don't remember the values you have to set it to. I think you set it to like 2 and 3 or something. 2 and I don't remember what the values are, but basically the idea is you get this to like exactly meet right there. I don't quite have it exactly meeting, but if there is numbers such that these meet exactly here, and basically the point there is undefined. And so this is called a degenerate elliptic curve, at which point you can no longer use it for cryptography. Otherwise, some bad stuff happen. So yeah, don't do that. But yeah, so you can also see here, this demo provides a handle for P and Q, which is kind of weird. It's not clear exactly what these do, especially if you're not familiar with ECC. But you'll notice that when I drag it, the Desmos demo is like basically drawing a line through the 2 points. And no matter what, provided that my elliptic curve is well formed, if I have 2 points on an elliptic curve, there will always be a third point that passes through the line that is secant to those points, or passes through both of those points. So any line that passes through an elliptic curve twice also passes through an elliptic curve 3 times, unless 2 of those points are the same point, in which case it's tangent to the curve and it only touches the curve twice, or it just misses the curve. But yeah, anyways, the reason why this is important is because we have, I mean, they kind of talk about it here. You can see kind of some descriptions of how this math is working out. And you could try to decode this. I'll talk a little bit more about this point addition, because that's what this is. Basically, if you have a point P and Q, there is always a point R related to those 2 points. Just keep that in the back of your head, and we'll kind of just move on from here. So feel free to keep playing with this time. Here we go. Awesome. So our goal here, after messing around with the curve, is to somehow take this concept of adding points along the curve to create the needed trapdoor function. And this might traumatize some of you that have taken Math 100. The glue that we need to do this is called group theory. So don't worry, you don't have to get into groups. This is not one of your like GEs. And we're also not going to dive super deep into group theory, because God knows that that rabbit's hole is endless. Yeah, breakout rooms. That's what I'm talking about, Tony. Everybody get into groups, you know. So that's essentially what they are. But yeah, so all I'm going to do is offer a brief coverage of this. Basically, what I'm trying to hit home with you is that a group is a set of elements with a closed operation. That's all it is. So A, B, and C, and even addition can be anything as long as A, B, and C are all in the same set. So A, B, and C are the same types of things. They don't have to be numbers, but they usually are. And plus can be whatever funky operation we want, although usually it's standard addition. And there's really interesting things that we can do with sets and operations that meet this requirement of being in the same set or being closed. One of which is that you can apply the discrete logarithm problem to it, which, as we saw earlier, is an example of a trapdoor function. So moving on, just a quick example. Again, integers and addition is just adding 2 numbers and getting a third number. That is a group. That is the world's simplest or most intuitive group. Vectors in addition are also a group though, right? You know, so if you've taken physics and you have like a 2-dimensional vector and you add them together, you just add up each component like component wise, and then both are closed, right? Because they take 2 elements from our set and produce another element that could also be a vector. So 2 vectors, add them together, you get another vector. That's another group. That's a standard group that you might be used to. So math majors, please stunt. I would like to see answers in the chat. Which of the following are groups? And I will go over these answers. If you are not following, don't worry about it. There's plenty more for you to enjoy in this discussion, but bombard me in the chat. Which of these is a group? My mom is a group. That was a good one. I don't know if that's true. I think my mom is one person, but I'll ask her later. A group, one option is A, which is addition over integers, which we kind of just talked about. Option B is multiplication over the integers. So let's take that funky form of addition and just call it multiplication instead. Are we still closed, so to speak? And then multiplication over the rationals, which is all numbers of the form P over Q. So any kind of fractions are supported by that. This one is a little tricky, but the key here is that, yes, you're totally right, it's A. And the reason why is because we just talked about it. Addition over integers is the prototypical group, right? But what's not so obvious is why these other groups are not technically a group at all. So the problem stems, so with the second one, multiplication over the integers, basically, you also have to have this idea of closure, which implies this idea of inverses, right? So in other words, what numbers is equal to, what times what is equal to 1? Well, there's 1 times 1, but you could also try to write a formula like 2 times what is equal to 1. And the problem there is that, 2 times 1/2 is equal to 1, but 1/2 is not an integer. So A, B, and C are not all part of the same set. So you essentially lose your closure there. And then C is a little bit even more subtle because rationals extend integers so that multiplication is a group operation, right? You have 2's as well as 1/2s, but where it breaks down is that you, of course, have 0, as Marcelo notes. 0 means that there is no inverse of 0 no matter what. There's no fraction that you divide by, divide by 0, it's undefined. So that's not a group either. But in actuality, if you take the rational numbers, all of them, and then remove 0, and then use multiplication on it, that's a group. That is a valid group. As long as you make the assertion that you have removed 0 from the set, it's a valid group. Okay, so that was just for fun. It's actually not that relevant. The point is that I want to introduce to you that something we've talked about is also a group, and that's elliptic curve point addition, surprisingly. Give me just a moment. Let me send a quick message, and then this will take like 2 seconds. But feel free to read this image real fast and take a look at what that looks like, because I think it's a pretty good definition of what it is. It's a 3-step process. Perfect. There we go. All right. So yeah, the first step is essentially, how do we do set definition? If we're trying to form a group out of elliptic curve addition as defined by this infographic, first, you have to understand that the things that you are adding together are points on an elliptic curve. I'll get to identity in just a second. Points on an elliptic curve, right? So those are kind of, you could think of them as vectors, right? Because they're just pairs of numbers because they're XY coordinates. And not every possible pair of numbers is a valid point on the curve because the point has to actually lie on the curve. You can't talk about points that aren't on the curve. So it's a little bit interesting. But given a curve and given X, there is a Y that corresponds with that X is another way to think about it. Or actually the other way around. But anyways, so you have your set definition, and then you also need your add definition, which is described by the infographic. Is there a way to add them together to get another point? And the answer is yes. You do a tangent line. You end up passing through the curve in 3 points. The third point, just reflect it on because keep in mind, elliptic curves are symmetrical, right, about the x-axis. You reflect it over the x-axis, and that third point is the sum of the 2 points that you started with. For some reason, I won't prove it to you rigorously, but this totally and completely satisfies the definition of a group. There's closure. For some reason, all of this together creates a group. Martin brings up a good point, which is, what is the identity? What he's referring to is, it's actually not 0, right? Because keep in mind, we're talking about pairs of numbers. For some reason, in the context of elliptic curves, it's useful to think about the identity as infinity. And that will make more sense, like literally the pair, infinity, comma, infinity. And that will make more sense with another demo that I have here coming up pretty soon. But yes, because since 0, 0 is probably not a point on the curve, your identity has to be infinity instead. But but it does kind of make sense if you think about the property of, yes, you bring up a good point, Marcelo, infinity is not a number. But here's the thing, we have left the realm of numbers. We are in the realm of groups. Our sets can contain infinity as a value if we want it to, right? It's just a piece of notation, a symbol that we use to describe a particular, anyways, we're getting too abstract. So performing elliptic curve addition without a modulus, right? This is kind of me coming back to that idea of the modulus that I talked about before. And I will also talk about why floating point doesn't mess it up. It has to do with the modulus. We're only talking about integers, as it turns out. So we need a modulus when we're talking about elliptic curves in order to prevent the points from increasing without bound, right? Because you could add these points together and get bigger and bigger points on the curve until finally it just explodes. Performing elliptic curve point addition without a modulus means that we could potentially need unlimited storage to hold our points, and no one has unlimited storage. So to limit this growth, we apply the modulus to our calculations. That means that after every integer addition, subtraction, or multiplication, we take the result mod m. And if we use an n-bit modulus, a modulus with n bits, an elliptic curve point will always fit in 2n bits of memory, right? Because if you have basically it's a pair. Each one has n different values. It could be 2n. That's all it is. It's that simple. But more importantly, as it turns out later, there are certain security assumptions that will only hold if we are using a correct modulus. And on the general case where it's unrestricted, these same security restrictions do not hold because of things like infinities and floating points and not a number and all that kind of stuff, and a bunch of other subtle issues not having to do with computation. But this may be seen as a totally left field obscene question, but I'm going to take a hard turn here and ask you this question. This is relevant, I swear. What is 6 plus 9? Now let me give you, no. Let me give you your choices. Let me give you your choices. Very clever, very clever. Here are your choices. Your choices are A, 1, B, 2, C, 3, and D, 4. All right, go ahead. What is 6 plus 9? You have 4 options. Come on, guys. It's not a trick question. Just answer. Now, a lot of you are probably looking at me and being like, Aaron, this is a totally unreasonable question. It's obviously but what I'm proposing to you is that you don't even need to know the mod because you have done this exact addition probably a dozen times in your life. Think about when you have done this exact addition in your life. Someone try to guess. Someone try to guess. I do this all the time. I literally do 6 plus 9 equals one of these values, probably I don't know, once a month. Okay, I'm not making sense. Great. The answer is 3. Why is the answer 3? Okay. I think there we go. Okay, I've got a few vaguely close enough answers, but yes, David basically has the point. It's a clock. It's not an unfair question for me to ask you that 6 plus 9 is equal to 3, because odds are this is the most common form of modular arithmetic you do in your life, right? If it is 6 o'clock, what time is it going to be in 9 hours? It's going to be 3. Yes, okay. Those of you used to military time, okay, I admit that this question is perhaps a little bit unfair to you. I apologize. But I still think this illustrates a useful concept. I mean, we could definitely abstract this to the military case. But for my purposes, I wanted to I assume most of you have seen a United States clock before. But I use this all the time. If I go to bed at 6 and I need 9 hours of sleep, I wake up at 3. Although probably I wouldn't use that sleep schedule because that sounds awful. But you've definitely done this before, especially if you live in the US. But this is modular arithmetic. This is all it is. Once you go fully around the clock, you're back to where you started. And the reason why we care about modular arithmetic is, as mentioned, it's basically a way to restrict the size of numbers without losing the ability to do operations on them. And I've been taught modular arithmetic so many times in my career, math and science and all that kind of stuff. And it's never really made sense to me until I came up with this visualization. So hopefully this is as valuable to you as it was to me, or maybe you already got it from the beginning because you're a lot smarter than me. Who knows? But let's say we have the numbers, right? These are some classic numbers that you've probably used before. These go on infinitely. There's an infinite number of numbers here. Just if you follow the ellipses, this goes on into infinity, the number infinity. And you can think of the mod, the modulus operator, for example, mod 7, as being this universe instead. So the top universe is the integer universe, which we refer to with the letter Z that's kind of got a double line down it. And we refer to the bottom universe as the mod 7 universe. And there's two interesting facts about this. For one thing, I want to impress upon you that the number of numbers on the bottom row is the same. There is still an infinite number of numbers. However, we now only need 7 labels, 7 different possible labels to keep track of an infinite number of numbers. The number of unique numbers is not the same. But the point is that you can still do operations on this, specifically group operations. And in fact, I'm going to say this without proof because it's a little complicated, but if your modulus happens to be prime, you actually meet the set of numbers, you meet the requirements such that this new set of numbers, the 0 all the way up to 6 and then repeating, that set of numbers, you can do addition on it and it's still a group. It is still a group and it will behave in all the right ways and it will have the discrete logarithm problem and all these other mathematical things that we've proven for groups in general. Whereas now the computer only has to keep track of 7 different values, right? So this is now realistic to do this kind of discrete logarithm problem on a very small set of numbers. Because now we don't have to expand into infinity. So to maybe impress upon you how modulus interacts with elliptic curves, I have another demo for you. It's acmurl.com/modecc. I'm going to go ahead and pull this up in my browser as well, so you can just follow along if you're feeling lazy. acmurl.com/modecc. And I'm going to leave the page. www.com. So in this demo, what you're essentially seeing is an elliptic curve, but only the points on it modulo some prime, right? So you can put in a non-prime value in here, but you're going to have a bad time. It's not going to be very useful. And it'll warn you. It'll be like, that's not prime, therefore it's not a field, which is a specialization, a special type of group, and your points are very orderly and it's not very interesting. You've got undefined values everywhere, right? And this table of point additions here gives you a great description of that because you end up with a lot of not a number values. Marcelo, a field is just a special kind of group, but we can still refer to it as a group. It is a group. Yes. So yeah, if I change this to a prime value, someone think of a prime greater than 300. Too slow, 307. That is a prime. I was right. I was also lucky. I did not know ahead of time if that was a prime or not. So now we've got, this is kind of hard to see, I'll admit, because I'm streaming, and so perhaps this is a little unfair to you, but hopefully you can see like the tiny red dots on here. These are all the points on our elliptic curve. These points all occur at integer intersects, right? Because the only possible values are 0, 1, 2, all the way up to mod 307. Like, you know, 1, 1.5, 1.5 is not possible. That is not a possible value. And now when we scroll down to our table, we'll notice that once again, we have the table of multiplications. But now, actually, excuse me, this is the table of additions. But now there's no nans or not a number errors in our table. We have instead a different pairwise addition for every single possible point, right? So this increases 0, all the way up, and this increases all the way up. And these are all the valid points that are on the curve. And you'll notice that infinity in this case behaves just like the identity, right? There are certain points where you add them together, and through the calculation of what the third point is, you get infinity. But that's actually okay. That's just another way of saying 1. It's kind of complicated, but you can mess with this and get it to show you some cool things. I can even, oh, that's not what I wanted. I wanted the Desmos calculator. You can even apply mod to this curve, and yeah, infinity. No, it doesn't flip it. If you multiply a point by infinity, you get the original point back. Look at the addition table. I keep using multiplication instead of addition, but look at the addition table. You can add infinity to a point, you get the same point. So you can even do like mod on this curve, and you can pick like, I don't know, 307. Aha! I actually did it right, which I wasn't sure if I was going to. But now you can see that this behaves a lot differently. This behaves a lot differently when you mod it. Essentially, instead of the curves expanding into infinity, now they repeat in kind of this band that lags your computer if you try to load this. And so basically now you've got like this, you've got a lot of points that are valid and on this curve, and the graphing application I'm using right now can't really handle what I'm trying to show you. Use that other example if you want to see it, but so for now I'm just gonna abandon this web page before my browser crashes, and we're gonna go ahead and keep going. But Marcelo, I'll leave it to you to answer your own questions with some more demos that we're gonna come up with later that will allow you yourself to do some addition and subtraction and all that kind of stuff on points on an elliptic curve that is modulo some prime. So you'll be able to see for yourself that this is in fact a field, which is just a type of group. Is that good? It's complicated stuff. Well, look, I'm not pretending it's easy. I'm not pretending it's easy, but some of the examples that are coming later will be more descriptive. I just kind of wanted to give you an idea of, hey, this is still a group. You have all of these points that land on this curve, modulus some number, and then you have an addition table that looks just like a multiplication table in that you have units and all that other stuff. So, but it has some really nice properties. So one property is the property of multiplicative inverses. And when I say multiplicative, I kind of mean in the context of elliptic curves addition. They get kind of used interchangeably, so bear with me here. But yes, so because you have this field of points and a unit that operates on them, you have the concept of inverses, right? So addition is clearly a group on integers, mod some prime, right? But what about multiplication? Does multiplication meet that condition, specifically not just on integers? We talked about multiplication and integers not being a group, but what about multiplication on integers that happen to be mod some prime? Well, the surprising result is that, yes, this is a group. There are inverses for every possible value. So let's use this as an example. What is the inverse of 3 mod 7? And when I say the inverse, I mean this is the technical definition of an inverse for groups that are modulo some prime number, right? So A and B are referred to as the multiplicative inverse or of A. Okay, yeah. So B is the multiplicative inverse of A mod n if A times B is equal to 1, right? In the same way that 2 times 1/2 is equal to 1, therefore they are inverses of each other. If you do mod something, oh, I've got one guess, or maybe it's a highly educated guess, that the inverse here is 5. And if you haven't messed around with modulus before, like that might seem weird, but it will make sense once I show you based on this definition that does actually work out. So the answer is 5. To see why, literally just take 3 times 5. What is 3 times 5? Well, it's 15, right? But we're in mod 7. So you have to subtract. No, radicals do not work. I know what you're talking about, but not everything gets abstracted out magically, but there are certain things, like, so for example, exponentiation is now, if you meet this requirement of having multiplicative inverses, you can do exponentiation as well as logarithms. But certain things like radicals do rely on kind of like a further extension, which I won't get into. I'm not that good at abstract algebra. But 3 times 5 is 15. You subtract 7 and you get 8, and then you subtract 7 again and you get 1, right? So we basically, by going 3 times 15, we went around the clock twice and arrived at 1. So therefore, 3 times 5 is 3 and 5 are inverses of each other in the mod 7 universe. So another thing is that we can write it like this. 3 is literally congruent to the inverse of mod 3, or excuse me, 3 mod 7. So, but we can think of this as division, right? So in the mod universe, we can think of dividing by 3 as also multiplying by the inverse of 3, which in this case happens to just be 5. So we can use that trick to kind of simplify things. So for example, if I take, what is the inverse of 1/2? Well, it's 2. It's the same as like flipping it from the denominator into the numerator. It's the same concept here, only now instead of radicals, or excuse me, not radicals, rationals, you're talking about whole numbers, and that still works out because modulus is like magic for some reason. It's really complicated. I highly recommend you take like either an abstract algebra class or a cryptography class that kind of will explain this a lot better than I am right now. But so with that said, we get to one of our first hands-on portions. We're going to try to bridge the gap between this idea of modular operations and the elliptic curve cryptography that we've been talking about, that we say we can apply clock arithmetic to. And so for that, I have this exercise. However, I don't recommend you do it. I literally don't. You can look at it as a reference, but basically this challenge is broken. Just letting you know. I still made it available to you so that you can look at it, download it, read it in your spare time. But these are essentially the exercises that myself and David Dempsey created for our original elliptic curve cryptography workshop back in the good old days. And the reason why this is broken is because the platform that we were using, Replit, is now covered with paywalls. So they've completely disabled my account, and I can't create, like, basically we had it so that you would write your submission and then it would auto grade it for you, and it would tell you whether or not your submission was correct or not, just like you're used to on maybe your CS homework. But because Replit doesn't support that anymore, I'd have to move it to like Stepic or something. Yes, Replit is totally paywalled now. There's almost no way to use it for free and share things. So in fact, even if you want to use this, what you have to do is, let me leave this page. What you got to do is, sorry, my browser's hanging because I just closed that stupid Desmos window. Oh my gosh, do you see it? Okay, there we go. Okay, so now that we're here, if you want to open this, you're going to go to Cyber Imp, and then it's going to make you like, basically it's going to make you log in, and then you have to press the button that says fork in order to create a workspace that looks like mine here. So you can still use that link to get the same workspace as me, but I'm not going to be able to see your submission, and also you have no test cases. So instead, I'm going to kind of guide you through what the original idea of this challenge was. Very close, Zenas, very, very close. You're way ahead of us, but I'll go ahead and dive into what this exercise would have looked like originally. So the idea of this exercise is we challenge you to, in Python, write a function that allows us to calculate the inverse of a number modulo a prime. However, what's really interesting is that we do give you some pretty explicit instructions on how to do this, though some of the images are broken. So this function down here where it says to do replace with your own code, this is the part that I want to like basically finish. However, so there's a couple of reasons why we implement the pow mod function. Zenas is right. Python's pow function already supports modular powers, but we went ahead and implemented here just to show you how easy it is. It's really not a complicated function at all. You can do it in just a couple of lines. And you can dig deeper into this by reading the Wikipedia article and all that kind of stuff. So the intended solution is, and a lot of the images that were originally in this markdown are broken. Let me see if they even show up here. No, it totally stripped the images when it booted me out of the classroom environment. So again, our goal is to take in a number and then determine its inverse mod this value. However, we are given the benefit of the doubt that mod is in fact a prime. So normally we would have to do something called the extended Euclidean algorithm to determine the inverse of this number. But because we know for a fact that mod is prime, we can actually use an even simpler solution to do so. And I encourage you to read about this. But by using Fermat's little theorem, which basically, let me see if you can see this, says that some value raised to the p power is itself mod p. And then down here, we can see that a raised to p minus 1 is equal to 1 mod p. If you basically continue this pattern, you can imagine that a to the p minus 2 is equal to a to the negative 1, right? So in other words, a to the p minus 2, as long as p is prime, is its own inverse. And it's not easy to see that by with me just verbally speaking it. But because of that, we can take advantage of the pow mod function that we've written here. Again, I am glossing over this, so I apologize. To do something along the lines of pow mod, we take the base, which in this case is our number. We take the power, which in this case is mod minus 2. And then we take the mod, which is just mod. And this should return the inverse of that number. So I can run this and it won't give me any errors. And I can even call this function on numbers. So I can do like inverse of mod prime. What's the example I showed earlier? What's the inverse of 3 mod 7, right? So I can pass in 3 and 7, and it'll give me 5. So that's how I know it worked. So yeah, we had a whole testing suite that would throw in these crazy values and show you all the ways that it could break or not break or whatever. But this is supposed to be like a short little exercise. And there's also supposed to be images in here that definitely help you get to the answer faster. So I'm not going to linger on this any longer. It's kind of a broken thing. I need to move it over to Stepic, but thank you for your patience. Any questions before I jump back into the presentation? Okay, I'm jumping in, but I'm still watching the chat. So if you ask, I'll try to hit the brakes. So once you implement inverse mod prime, the second thing that builds off of it, because I got to admit, that didn't really build off of elliptic curves at all. So now let's take that and apply it to elliptic curves. Let's implement elliptic curve point addition using the function that we just created and some of the aspects that were talked about in the slide before. So for this, I'm just literally going to hop back out into my browser, elliptic curve point addition. So the key description here is, let's see here. Yeah, so there's a suggested approach. And there was this snippet from Wikipedia that was saved as an image, but okay. Yes, here we go. Point addition. This is the Wikipedia article for point addition. So let's just use this as our reference. And honestly, that'll probably be enough. So we can even just put this over here and put this, whoops, I didn't mean to do that far. Put this right there. And we can close this, I think. let's just make it small. There we go. So using this definition of point addition, we are going to implement this particular function that adds 2 points that are on the curve and gives us a third point. So using that graphical definition, you can basically derive this formula that looks kind of like this. You really only have to calculate 3 values. You calculate lambda, you calculate xr, and you calculate yr, and both of them are functions in terms of lambda. Let me grab this. There we go. Okay, so it's actually not that bad. We basically copy over the description from Wikipedia, right? So for lambda, it says that's equal to qy, right? So, oops, in parentheses, qy minus py, and then we divide that by qx minus px, right? And then Rx is just in terms of that lambda. So we get like a lambda times lambda situation minus p of x minus q of x. I'm looking at Wikipedia here. And then technically what we want to do before we return it is mod it by the prime, right? So we do that with the % symbol. And then for the second point, we're just going to do the exact same thing. Follow the formula. The formula says to do lambda times p of x rx minus py. Yep, that looks correct. And then we're going to mod it by the prime. And there we go. We're done, right? Like that totally works. So does anyone see any potential issues with this formula here? Martin, I totally agree. We're doing this janky division. And everyone knows, who's ever done computational data science, that division is bad. It's slow, and we're very unlikely to get a whole value out of this computation. Instead, we're extremely likely to get a fraction, which the points on the elliptic curve are supposed to be whole values only. So we need to apply the fact that this is modulus in order to actually do this. So keep in mind, instead of dividing by something, we can multiply it by its inverse. And we have a function to compute that inverse, right? The one that we just wrote in the previous exercise. We pass in the number, the value of which we want to mod it by, or find its inverse mod with respect to a certain modulus. And this is essentially the same as dividing as before. It's going to give us the integer pair equivalent of what the division would have given us. And this is actually crazy fast. This is much more efficient than doing like a division. So this is actually a very efficient algorithm. So with this, we have basically the entire formula laid out. I'm going to go ahead and hit play. And I'm going to expand this back out. We don't need the Wikipedia article anymore. Now, if we wanted to test that this actually works, it would be kind of hard because we would need points on a valid elliptic curve. So for that, we can use the demo that we created earlier. What is it? Mod ECC, and use a very small curve where A is 1, B is 0, and the modulus is 13. And so if I go back to this exercise and I want to test out add EC points, the documentation here says that the curve has to be kind of like a tuple, which just means a bunch of values. That is your A, B, and your prime. So that would be 1, 0, 13. So 1, 0, 13. Your second value needs to be the point P. And for this, we'll just grab a point from the multiplication table, or excuse me, the addition table. So let's just grab 2 points from the addition table. Let's grab 3, 11, and let's grab 7, 8. Oh, wrong one. 3, 11, and 7, 8. And that spits out some value. It spits out 6, 1. So we go to our addition table, 3, 11, and 7, 8, and oh, there we go. We got 6, 1. So it looks like, via our very thorough evaluation of the function that we just wrote, that this point addition does in fact work. The math agrees. And so we can go ahead and say this is probably working the way it's supposed to. So yeah, if you want to see infinity or what infinity looks like, our function doesn't properly take it into account, but we can add 7, 6, or excuse me, 2, 6 and 2, 6 together. You'll notice that it occurs when you add kind of like, 2, 6 and 2, 7 are inverses of each other. So they produce the point infinity. So let's go ahead and do that. So the point 2, 6 and the point 2, 7, what pops out? 9, 7. Yeah, like I said, it doesn't account for it correctly because, oh wait, that's what it's supposed to spit out when it's 2, 6 and 2, 6. Did I typo it? No, I didn't. But anyway, it's incorrect. This function does everything correctly with the exception of infinity, which is in this implementation supposed to be represented by 0, 0. But there's reasons why it's not working. This works as long as you don't use the inverses for this one. So I'm going to keep going for now. You can hack on this later. David Hacker would definitely be able to answer your question a little bit better though. So moving on, we're going back to the presentation and away from the coding. Thank you for your patience, by the way. I appreciate it. Yeah, so moving on, we have elliptic curve point multiplication. So I've been using the words multiplication and addition interchangeably, but I really mean multiplication. Up till now, we've been doing addition, right? So, but now I really mean point multiplication. We already know how to add points. So potentially an efficient algorithm for multiplying points is to just add n times, right? So you have this point P, and if you add it to itself, you're going to get this point here, which reflected on the x-axis is 2p down here, right? And then you go 2p through itself, you're going to get 3p, 4p, 5p, 6p, so on and so forth. So basically, when you multiply this point, it's going to just start bouncing around this elliptic curve a bunch. And that's great. That makes it unpredictable, which is an important aspect of its security for the purposes of cryptography. But yeah, so as it turns out, we can actually do a little bit better than just multiplying by n times. Say we have an integer n and a point p. We wish to perform multiplication such that we get another point q that is the product of n and p, where n is an integer and p is a point. In other words, q is p plus p plus p plus p plus p. And like I said, there is a naive way to do it, but it's O of n, if you know what that means. And surely we can do better. And that's only assuming addition is constant time, which we know it isn't. It's about log n. So yeah, let's see how much better we can do. So I propose a new algorithm to multiply points called the double and add algorithm. However, those of you that have taken CSC 21 will probably recognize that this is almost completely identical, and in fact is actually totally identical to the multiply and square algorithm. If you don't know what either of those are, don't worry. It's not that complicated, and I will walk through it. In fact, the entire algorithm fits on this slide. It's already there. Basically, the idea works like this. If n is odd, we are going to compute the point p times n minus 1 and then add p to that. Hopefully you agree that that is equivalent to just multiplying p times n. So what's the advantage of multiplying p times n minus 1 instead? The advantage is that if p is even, or excuse me, if n is even, which we can accomplish by subtracting 1 from n in that way and doing an addition to pay for that. If n is even, we move on to the second step here, where we can instead have n by 2 and just multiply the resulting point by 2 instead. And so the way this algorithm, the base case, the code I'm going to show you in a minute will kind of show you what the base case is. But the reoccurrence formula is if n is odd, we compute the top one. If n is even, we compute the bottom one. And if you have been taking CSC 21, the master theorem says that this runtime is, does anyone know? Anyone know what the runtime is? It's the same runtime as the multiply and square algorithm. It is in fact O of log n. It is, I wish it was constant time. That'd be awesome if it was constant time, but we do, basically we're having the number over and over again. O of 0, that would be very impressive. Okay. So there's an exercise that walks you through the implementation of this algorithm. It's at acmurl.com/cyber ECPM. I don't expect you to do it. Instead, I'm just going to quickly demonstrate it. It's even faster than the last exercise if you know what you're doing. So I will kind of show you. Let's see here. Yep, it's this one. Great. So what we're going to do is basically implement exactly what it says to do here, which is, if d is equal to 0, return 0, 0. Oh, by the way, this function multiplies, given a curve and a point P, it multiplies it by D. So we're using the number D instead of N from our slides. But this is basically a suggested approach. And then there's a few extensive, if you want to like challenge yourself and really know the material, you can do it recursively instead of iteratively, or excuse me, vice versa, to make it a little bit more challenging. Wikipedia has details, or you can implement a different version of this algorithm called the Montgomery ladder, which is actually used more in practice, but it's a little bit more difficult. We'll talk about it briefly, but not dig into it too much. We'll see that we're given a few resources to be able to accomplish this. We're given the add EC points function from another file and the double EC point function, which both of these functions are, well, to be more precise, the add EC points function is the same function that we implemented in the last challenge. So we're still building off of things that we had before. But these are, the add is what we do in the odd case, and the double is what we do in the even case. So if d is equal to 0, we return 0, 0. If d is equal to 1, we return the original input point p, right? Because we're multiplying it by 1. And those are the two base cases that we need to cover. Else, we just cover the even and odd cases. So I'm actually going to extend this else statement to check to see if d is odd, which we do using this operation. And then what we can do is we can compute an intermediate point q that is essentially applying the same function we're in recursively, point scalar, curve, we pass in p and we pass in d minus 1, right? Because we subtract 1 in the odd case. Once we have the point q, we just have to add the point p to the point q, and we have a function that does that. So add EC points. It's the same one we wrote in the last one. We pass in p, we pass in q, and we're done. Minus the fact that we now have to handle the even case. So we just put an else for that. The even case is even simpler. We just do multiplication EC point scalar. So we do the recursive call. We pass in the curve because we need it. We pass in p, and instead of subtracting 1 from d, we have it, right? And so once we've halved d, how do we know that this is an integer and not a floating point, right? Because it's even. We know it's even. And in fact, we could even do some like bit magic if we wanted to. We could shift this over by 1, but I'm not going to get that fancy. So we're just going to divide by 2, and Python will probably figure that out and do it anyways. Double C point in the even case, just like that. There's the curve, there's Q, and we're done. Literally, we finished. Okay, great. And this probably works, but I actually don't have example points on hand or even readily accessible that I can use to verify this. So take my word for it. It worked. I mean, I could throw in some points and I'll get an answer. I just won't know if it's correct or not. So, but this should be effectively the algorithm. And you can always come back and watch the video if you are interested in verifying its behavior independently from me. Any questions on this before I jump back into the slides? That was the last exercise, by the way, if you can tell by my number of tabs. I'm also running out of coffee, which means we're definitely going to start closing out this presentation soon. I just have a few more things to talk about. Also running out of hunger. All right. I also have not eaten in a hot minute, so I will power us on through. Thank you so much for your patience, as always. Okay, So I did mention the Montgomery ladder just now. Turns out that the original algorithm that we just implemented, double and add, is vulnerable to some side channel attacks. Side channel attacks are this interesting idea where basically, well, let me describe it very specific to this scenario. We perform one addition, right? Every time we see a 1 bit or the number is odd, and then we perform a multiplication whenever we see a 0 bit where the number is even, and we kind of iterate that way. And so because of this, if we are able to somehow keep track of the number of additions, we could do things like measure power consumption by the computer or single out additions or try a bunch of values and see how long it takes, and basically disconcern what the original values were, right, of P and Q. And so that's a big problem, as in not to you and me, right? Because we're not implementing enterprise grade security, but side channel attacks are a very big deal in like the government and nation state actors and all that kind of stuff. So this is a very real thing that needs to be solved. Fortunately, there is a very easy solution. There's an alternative algorithm where you do adding and doubling regardless of whether or not it's even. The only difference is the number and the way that you swap them around and move them. But basically, regardless of how many ones or zeros your number has in it or what your number is, the Montgomery ladder is going to do the exact same number of operations in order to arrive at the solution, and is actually still big O of log n. So this is the algorithm that's more frequently implemented for the purposes of preventing side channel attacks. But I just thought I'd throw that in for fun. So how is this cryptography? We're here, we're there. We're at the slide that explains why this is cryptography. The reason why this is cryptography is because of the ECDLP, which is the elliptic curve discrete logarithm problem, which is as simple as this. You can write it down on this slide, right? Given P, Q, and you know that Q is some multiple of P, find out what N is. And keep in mind, N is how many times we're applying that multiplication, but it's not constrained to our modulus. So our modulus can be relatively low. Our modulus can be 307, but we're still gonna have a really hard time determining what N is because it could be 1 billion. And it could go around on this system so many times that we completely lose everything. So turns out that this problem is extremely hard to do, even harder than integer factorization. The best algorithm that can solve this problem is an exponential time complexity algorithm, which means for any substantial values of n, you could pick a value that just makes it basically completely impossible. So n can be anywhere between the value of 2 and m-1, where m is your modulus, and that can be almost an obscene number of cases that is very computationally difficult to check all of them. There's no shortcuts like there is with integer factorization. And the reason why this is cryptography is because that is a trapdoor function, right? This forms the basis for all elliptic curve cryptography cryptosystems. That's a mouthful. This is our trapdoor function. The private key in this case is n, but there's a lot of different schemes that use different ways of determining like different private keys schemes and all this kind of stuff, but it's based around this problem. Different ways of deriving private keys and public keys. But at the end of the day, the core of it is that this is very difficult to undo without prior knowledge of what n is. Okay, so let's talk about good curves, because as it turns out, not all elliptic curves are created equal. There are a lot of possibilities for what A and B in your elliptic curve can be, and M for that matter. And different choices have different properties from the perspective of security as well as computational time. But you have to be like a serious freaking math magician to be able to kind of understand what's involved there. People also do use other kinds of curves than the ones that I've shown you, although they kind of have the same properties and are solved the same way. For example, there's a curve kind of called the Montgomery curve, which is a slightly different function. You've got 3 x terms, 1 in the 3rd power, et cetera. And the curves that generates look even crazier. And there's even a website that publishes a bunch of curves that are quote unquote safe to use, of which there are, a few documented options. And a lot of those have like historical backups to like why you would want to use that and who's used it in the past. Yeah, safecurves.cr.yp.to. It is in fact very safe, except for the backdoor thing, which I'm getting to, Martin. I have a slide on that. Don't worry. I'll talk briefly about that. But that has nothing to do with using elliptic curves for cryptography. As far as we know, it's not easy to backdoor that. But there's a specific implementation published by the NSA that does have a backdoor in it, but none of the other curves are used that way. So anyway, moving on. Why elliptic curve cryptography? Well, as it turns out, breaking a 24 or 228-bit RSA key, which is the other very widely used, in fact, more widely used encryption standard, that takes about the same amount of energy required to boil a teaspoon of water, right? If you wanted to crack that. So that's something that even you probably have access to in your home computer. So breaking a 228-bit RSA key is not that hard. Whereas, and then that's using conventional computing techniques, so no quantum computers, which would probably take more at this point, but at some point it would be more efficient. Whereas if you were to have a key that was the same size, but for an elliptic curve crypto system, so 228-bit elliptic curve crypto key takes the same amount of energy required to boil all the water off of the Earth. So this is completely inaccessible for humanity. Like literally no amount of computers that we could build without causing like a thermonuclear destruction of our planet will ever be able to crack something that can literally fit on a Post-it note, which is quite insane that you can get that much security from that much information. Because when you think about it, like compare that to a OneTime Pad, where you need a OneTime Pad that is as big as the original message you're trying to solve. If I have an ECC key that is small enough to fit on a Post-it note, I can encrypt everything repeatedly. I can show other people my public key and it doesn't matter. And you can literally never impersonate me or read my messages. And that's absolutely astounding. So the highest ever broken RSA key ever is around 800 bits, whereas the highest broken elliptic curve key is only around 100 bits, which means that in practice, most RSA keys in usage today range somewhere between 1,000 to 4,000 bits. In contrast, elliptic curve keys can get away with only being 192 to 512 bits long for the same level of security. So from a network efficiency standpoint, it's much more useful to use elliptic curve cryptography, and I highly suggest you do it. If you don't believe me, use OpenSSL to generate an RSA private key and an ECC private key and compare them. The RSA key will probably take up 10 lines and the ECC key will probably take up 1. Anyway, moving on. This is the topic that Martin was subtly hinting at. Although it looks like a bunch of gibberish, we're definitely approaching C++ style abbreviations with our slides here, and I apologize for that. So this standard, dual EC DRGB, I don't remember what that stands for. It's just some government label attached to a particular implementation of elliptic curve cryptography used to create, it was basically presented to the world as a way to generate cryptographically secure random numbers by using the properties of elliptic curves. But there were a lot of problems with this right off the bat. This particular algorithm that was published was by someone was astronomically slower when compared to its equally secure counterparts, right? Which when you're looking for a hashing algorithm, you want slow, but when you're looking to just generate random numbers, even if they're cryptographic random numbers, you want it to be as fast as possible, basically. So being slow is not helpful. But more importantly, there was evidence that this particular algorithm that was published could be used to house what is referred to as a kleptographic backdoor. Has nothing to do with the phrase kleptomaniac. Kleptographic means that not only could there be a backdoor, but there's no way to prove whether or not there is one. Whoever created that backdoor, if it exists, has infinite plausible deniability. There is no way to prove that a backdoor was inserted, but if there is one, we'll basically never find it. But so despite all these problems and people discussing these problems, the National Institutes of Standards and Technology, NIST, which is a government-related organization, standardized it officially in 2006 as something that you should do, right? In fact, they provided a set of required parameters specifically that were 2 points chosen on a particular curve. And it is theorized that these 2 points contain a backdoor and are related such that P is a multiple of Q. And the reason why that matters is it's impossible to prove that P is a multiple of Q because of the elliptic curve discrete logarithm problem that we talked about before. It's a trapdoor function. There's no way to prove that one is a multiple of it. I mean, if the suspense is killing you, I'll go ahead and ruin the fun for you. The 2013 Snowden leaks basically confirmed that the NSA created this algorithm and slipped a backdoor into it. So we basically have hearsay confirmation that yes, there is a backdoor in this function. Or to be more precise, there is a backdoor in some kind of government-sponsored elliptic curve random number generator. But this is also one of the only ones and is the only one capable of supporting that. So we basically know it's this one. So yes, to quote the article specifically, the actual document that was leaked, it says, the goal of this was to covertly introduce weakness into the encryption standards followed by hardware and software developers around the world. Why would the NSA do this? To spy on people. In fact, there's other organizations that do this too. The CIA own all of the cryptographic hardware companies on the planet, basically, and were recently, within the past like 12 months, revealed to be paying a lot of it, like slipping backdoors into the hardware of these technologies as well, so that they could spy on other countries that use them. So one thing that we're pretty good at is slipping backdoors into things. But let me talk a little bit about how this was first discovered. It was actually discovered by a couple of, well, I wouldn't say discovered. It was first brought to public attention by a couple of researchers from Microsoft that published a presentation called, these are the actual slides from it, on the possibility of a backdoor in the NIST dual EC-PRNG, right? And they did some experimental verification where they basically created their own P and Q values such that they were multiples of each other. And then given a large enough sample size of numbers coming from this random number generator, they were able to, with only 32 bytes of output, correctly identify the internal state of the pseudo-random number generator. And that's kind of like a lot of spiel. Why does this matter? Well, if I'm using a random number generator to create private keys, then if I can tell what the random number generator is spitting out, I can also determine what your private key is. And now I can read all of your, I have a decent guess at what kind of values you're using to encrypt your messages. So this is a big deal. This can break apart things like the public key cryptography systems that we've used prior, which rely on using some unguessable values initially as your private and public key. But that's only if you end up using this to generate those values. So if you don't use this to generate those values, you're probably safer. Okay, so this is a flowchart of the algorithm. I'm almost done. I've got like 2 slides left. So thank you so much for your patience. I know this is kind of a long one. The DRGB uses 2 fixed points, P and Q, on some elliptic curve. They do some process. This is kind of hard to go through. I'm not going to kind of step through this step by step. Instead, I'm just going to kind of cover what it looks like to take advantage of this backdoor. So let's say an attacker learns what R1 is, right? So they observe this part of the random number generator coming out. This is the one part of the observable part of the random number generator. And we also happen to know that P is a multiple of Q because we designed P and Q to be multiples of each other. So we know that magic value N such that they are multiples of each other. Well, we can observe the output of the R1 here to kind of guess correctly the top 16 bits for R1. And then we can find the full point by solving the elliptic curve equation with far less, oh God. So we can solve the elliptic curve equation to get the y value from that, because keep in mind, r is derived from the x value of this curve. We can then figure out the y value. So now that we have S1 times Q, how is this related to finding S2, which is another piece of the internal state that we need to derive? Well, we recall that S2 is just equal to x times S1P. But here's the thing, we already have S1Q. And if P is some multiple of Q, then we can just multiply S1Q times our previously known value to recover this value of, this basically is just maps times n over to what S2 is. So now that we know what S2 is, we should be able to predict what new numbers this generator is going to spit out. And I mean, at this point, we basically deconstructed the next state, because this thing's basically in a feedback loop, right? It takes some initial state that we don't know and then uses it to continuously generate random numbers. But if at any point we figure out these internal states, we can predict all of the random numbers that are going to come after it, right? And so we can use partial outputs to guess that and pretty quickly get the internal state, and it's not a big deal after that point. So yeah, that's kind of interesting. I kind of just tried to skim through that the best I could. If you're interested in what these kind of things actually look like, here's the actual points on this curve that are published by the government that may or may not be multiples of each other, particularly P and Q here. They give both the X and Y value at the bottom. They're so astronomically large relative to what you and I can understand that there's no way to evaluate in any reasonable amount of time if they are multiples of each other. So we just give up and hope they're not, or just not use this curve altogether. It's just a weak algorithm. So, anyways, this was just here as a curiosity. And with that, I am done. That was the end of my presentation. You survived like 60 some odd slides. I kind of just went all the way through elliptic curve cryptography without you even realizing it. I definitely, like I said, it was a kind of a vague flyover. But before you go, come close, like lean close to your computer. I have something to tell you. I have some news, okay, that you might not be able to handle. It might come as a shock. Do you think you can handle it? I don't think you can handle it, just to be clear. As it turns out, the dark secret of elliptic curve cryptography is that you've been staring at a donut the whole time. That's right. Elliptic curves are actually just donuts in 3D space. And you've been running around the surface of this donut to generate cryptographic values, when in reality, it's just a donut. It's donuts all the way down. Anyway, I just thought I'd share that. I don't have a good animation or visualization of this, but trust me when I say it's always a donut. That's why if you ever pick up a textbook that talks about elliptic curve cryptography, they usually have a donut on the cover because you generally understand it in terms of that. But anyways, so thank you all. That was a real ending now. Thank you all for coming. That's all I had for tonight. I really appreciate you coming out, taking time from your busy Monday evenings to listen to me ramble. I hope you all learned a lot. I'll stick around for a few minutes to finish my coffee, and then I'm going to sleep because I've been talking for 2 hours. And more importantly, you've been listening to me talk for 2 hours. I don't know what that's about. That's crazy. So yeah, that's all I've got for you. Oh my God, it's almost 8. What the heck? It's all donut, Yushan. It's all donut, and it always will be. It's always donut. I'm going to go ahead and stop the recording now.